Okay, everybody, today we're going to start our fourth and final unit, water systems, and we're going to start off by talking about water. So from a chemical standpoint, water is a single molecule that's comprised of two hydrogen atoms and an oxygen atom, and we call it H2O. You guys have probably seen that before. And because of where the electrons are in this arrangement, the water molecule isn't just a straight line. It's not like a hydrogen on one end, oxygen in the middle, hydrogen on the other end. The hydrogens actually get like kicked down a little bit, so they look kind of bent. If you're really interested in this, or I don't know, if you're really bored because of quarantine or something, you can just check out this link if you want. It goes into a little more detail than you need, but it does do a decent job of explaining why that happens. So because of its shape, water has a trait to it that we call polarity. So just like you've got the North Pole at one end and the South Pole at the other end, and there's a force um, related to those things, this molecule has that as well. Other molecules are polar, but it's very important that water is polar. So one side of it's more positive and one side of it's more negative. And this, along with a couple other traits that we're going to talk about, makes water very, very special, very, very important. From a general standpoint, and I was very excited to make this lecture, water is amazing. It breaks some rules that kind of exist for most things, and life as we know it, maybe life would exist without water, but definitely not in the same form as we know it. So our first trait of water, or our first kind of exceptional part about water, characteristic, I suppose, is that water dissolves so many things. And I think I saw somewhere it said like water dissolves more things than any acid does, which I didn't fact check that, but I would believe it. I think that is believable. Water's polarity allows it to dissolve a huge number of other things, and it's because it's polar that it can do this so well. And we call water a universal solvent. A solvent is anything that a substance can dissolve in, and water is the universal solvent. And why this is so important is that in nature, um, everything needs nutrients and minerals and a bunch of other substances. And one of the easiest ways for that to move around the surface of the planet is through water. If it can dissolve in water, it can run down a river, it can go into the water system, and be transported all around the globe. But if you had just like, so say an animal needed salt and salt couldn't dissolve in water, every animal would have to go digging around and like mining salt, which would be extremely difficult. So our second characteristic is that water has a high cohesion, which results in a high surface tension. So this is again due to water's polarity. And this, in kind of regular terms, means that water sticks to itself. It's got an attraction to itself. And some insects use this to walk on water. But more importantly, or not more importantly, but maybe more fundamentally, nearly all plants would die if this stopped being the case. Because plants, I don't know if you guys have learned this yet in grade 8, they have these things called xylem and phloem, and they basically are like these tubes that from the roots all the way up to the tip top of the leaves, they transport water and transport food and stuff like that. And water, I think, is in some of their food, or rather, their food is dissolved in water, sugars, and so on. But those substances couldn't reach the top. The water or the phloem through the, or sorry, through the xylem and the phloem, the water couldn't go up there if it didn't have this surface tension, this cohesion. Because as one molecule of water gets moved up, the rest of them are, or the rest of the molecules behind it are kind of like attracted to it, and it kind of sticks to the walls, which is adhesion, and it sticks to itself, which is cohesion. And you've probably seen little droplets like this. Um, and that's solely because it has a very high cohesion. Not all liquids will do that. Some will, but not all. This is an important one, and this is one you've probably experienced and noticed before. Water becomes less dense when frozen. Most things become more dense when frozen. You guys learned molecular theory, I think, starting in like grade 4 or something, where you've got solid, liquids, and gases, and solids are closer together, and all the atoms in liquids are a little farther apart, and in gases they're very far apart. Water just doesn't follow that rule. Um, it's one of the only substances that exists in all three states at normal Earth temperatures, so we see it in liquid and gas and in solid form. And at solid, it floats in itself when it's a liquid, which is very, very strange. Most things, when they switch to a solid, are going to sink. So I don't want to go into the chemistry too much, but essentially, when ice is formed, the bonds are or the molecules are spaced out more than they are when they're in liquid, because of a bonding pattern. So I want you guys to think about this for a second. Water becomes less dense when it's frozen, and imagine a world where water becomes less dense as it freezes, and it's kind of scary. Anywhere that has ice, so like let's say the Red River or something, when it freezes in the winter, that ice, if it was more dense, would sink to the bottom, and then the top layer would freeze again and sink to the bottom. The top layer would freeze again and sink to the bottom, and eventually the entire thing would freeze solid, which would kill everything in it. Um, that's not good. So as it is now, the way it works is ice freezes at the top, 0 degrees, right? And then below there, you've actually got 2 degree and 4 degree water. The bottom of a lake or the bottom of a river generally stays at around 4 degrees throughout the entire winter, no matter how cold the winter gets, because you've got that isolating or insulating, excuse me, layer at the top. And the last one, this one's a little more scientific or harder to understand, I would say. Water has a high specific heat. So a specific heat is how much energy something can take up before it raises its temperature. And so with water, this means that the amount of heat or energy that's needed to increase the temperature of water by 1 degree Celsius is relatively high compared to other substances. When we say it has a high specific heat, we mean it can take up a lot of heat before it actually changes in temperature. So this means water will change temperature slower than most things, which makes it both a heat sink and a heat source. Let's talk about those terms for a second. Heat sink means that it's going to, say it gets really hot out, like right now in the summer. If we're by a large body of water, like if we live by the ocean, the land would heat up, and then the ocean wouldn't, and it would actually absorb a lot of the heat from the land. So it would actually cool down everything around it. And in the winter, you would have the land getting really cold, and then the ocean would still be fairly warm from summer, and it would actually start giving off heat towards the land. And that would be a heat source. So a heat sink is when it takes up heat, it starts absorbing heat, and a heat source is when it gives off heat. And this is noticeable if you look at temperatures of like maritime communities, you look at PEI or you look at Vancouver. Those places are surrounded or butting up against oceans, and their temperatures range much lower than Winnipeg, because Winnipeg's smack dab in the middle of the continent, right? There's no large body of water near us. The Red River is there, but it's not large compared to some of these other things. And you'll see these like extremely low variation of temperatures there compared to Winnipeg. We have a range of like 50 degrees or something. Um, and it's because they have these big bodies of water that are heating them or cooling them in the times that the land is cold or hot. Whoa, didn't mean to do that. There we go. So another non-intuitive trait of water. This is one that if you watch any TV or movies, you'll think I'm lying. Water is actually a good electrical insulator. Fairly good. It's a fair insulator. But that's pure water. So if we're talking pure water, we're talking pure H2O. However, water is almost never pure, and generally, like we said, is a universal solvent, right? So it's going to have a bunch of stuff dissolved in it. Generally, there's like salts and minerals that are dissolved, and all those salts and other stuff make it actually a very good conductor. The things in it are what are conducting electricity. The water itself generally doesn't conduct electricity, or rather doesn't conduct it very well. So I saw I saw a good quote on this one that said something like, even though pure water is a pretty good insulator, it doesn't take a lot of current to ruin your day. So, don't think that it is, like a perfect insulator or anything, and don't go touching wires or don't go touching buckets of water that have live wires in them or anything. It's still dangerous, but this is a fact that is very non-intuitive because we almost never see pure water. You can get it in labs and sometimes with like ionizers and stuff. So you might see it at some point. Okay, everybody, that's it for today. I hope you have a good rest of the day. Cheers.